Okay, good morning. So we go to the next topic, which is the second chapter. So we go back to this book, okay? So we start from chapter 2. So on Google Classroom, whenever I say do this from the book, I mean this Origo book. Okay, so we are on chapter 2 now. We want to talk about set theory. It's a very fundamental theory in mathematics. Everything in mathematics can be viewed as a set. Okay, but this is not hard at all. So I mean, this in principle should be very easy for you. Okay, so this is a very hard subject if you want to understand it deeply, but it is very simple because we have two versions of set theory. One set theory is called axiomatic set theory, and one of them is called baby set theory. So what you are studying here is not even a baby, it's an infant probably. So, but it's not that hard. So the notion of a set, I have used the notation of set theory before without formally introducing them. The first thing that we want, of course, to discuss about in the set theory is the notion of a set. Okay, but I hope that you understood from what we learned before, it is not the case that I can define every concept for you in any mathematical structure. Because what I want to define for a set might be, I can say a set is a collection of objects. Then you might say what a collection is. And I can say, okay, collection is a group of things. And then you can ask what a group is, you know. So it is not possible to define any term for you. So I have to start somewhere, accept it intuitively or based on uh, experience or whatever. And then that concept is called a primitive notion in the structure of mathematics. So the name is a primitive notion. A primitive notion, it means that I can describe what I mean, but I cannot define it objectively based on words that are more familiar to you. Yes. For example, if I want to say set is a collection, okay, collection is also more or less the same thing. Because okay, you have a better feeling of a collection of a group, but that is, I'm not solving any problem from you. So I can just describe what a set is and take it for granted, and then we can put some structures on top of that. Okay, so that is what we are going to do in this set theory. So what we can say about a set is that set is a collection or a group of very precise uh, objects. So it means that the objects should be defined properly. Okay. In other words, it's a collection of objects. It's a collection of objects for which every other object is either within my collection or not, without ambiguity. Okay. For example, I can say the set of the set, usually we say the set consisting of one-digit natural numbers. I consider this a good description of my set, because by reading this sentence, you understand what are the objects within my set. For example, is a desk in my collection? No. The collections are numbers. But for example, is 52 in my set? No, because it does not satisfy what I demand. Because I demand only those numbers are within my set that are natural and one digit. But 52, even though is natural, but it is not one digit, so it is not in my collection. But for example, I don't know, 7 is also natural and one digit, so 7 is here. Okay, a square root of 3 is not here because the square root of 3 is not a natural number. So this description is good. But if I say the set consisting of some of the one digit, some of the natural numbers, this I don't accept it as a good description. Because if I say, is 52 in this collection, you are not sure. Yes, because I have written the set consisting of some of the natural numbers. It is not clear, is it 52 there or not. So I don't want you to use this kind of, so this is not good, okay? It's a not a good description. Of a set. So we will avoid this, but that is a good one, okay? And now usually when you talk about sets, you use capital English letters to denote them. For example, I can set A, set B, or etc. And there are some punctuation rules that you have to follow. It's not subjective. Okay? Exactly like that when you finish the English sentence, you don't put a comma there, you put a full stop. Okay? That is the rule, that's a grammatic rule, so you have to follow. Punctuation rule that you have to follow. So here, if I want to write this set, I write the name of my set. If you prefer to have different names, you are allowed to do that. But let us say that I want to call this set A. Then I put equality sign, and then I have to open a curly brackets. No parentheses, no square brackets, just curly brackets, okay? And then put the members, okay? This is also the word that you need to know, the members or elements of my set within this, and then close the curly brackets and separate the elements by comma. So these are the punctuation rules. So for example, but order is not matter. It is not important to follow the order. But of course, if we follow order here, because we are more organized, it is better to be more organized. But that's not an obligation at all. So if I assume that natural numbers start from 1, so I would write 1 first, and then I have to separate it with a comma. It's a mandatory thing you to do, okay? You cannot just list the numbers without commas. So you have to respect that you have to put curly brackets, you write the numbers, the members in, and separate the members with commas. So here 2, 3, 4, 5, 6, 7, 8, and 9. And then when everything is finished, you close the curly brackets. So this is one way of representing what I wrote in words. This is the set of A consisting of those elements. If you prefer, you can reorder them. That's okay. Maybe we'll talk about that later. So you can write 2, 1, I don't know, 5, 6, 7, 8, 9. And 1, 2, 3 is, for example, 4 and 3. That's good. So that's also A. So here it doesn't matter in which order you put them there, but you have to respect, first of all, curly brackets and then commas for separating. Each one of these is called a member or an element. And if I want to show that an object is a member of my set, for example, 3 is a member of my set, this is the symbol I use. I have already used that a lot. So this, I will write this. And this is the Greek letter epsilon. So we say 3 belongs to A. It means that 3 is a member of my collection. Okay, and if, for example, a square root of 3 is, of course, is not in my set, I denote it by this symbol. So this means the square root of 3 does not belong to A, but 3 belongs to A. So that's the way that I actually denote it. Okay. Sometimes, of course, if I want to say the set consisting of natural numbers, so then what should I do? The set consisting of natural numbers, or of course I can say the set of natural numbers. Yes, so what should I do? I call it later, but I can open a curly brackets, then I have to list the numbers there. But how many of them are there? Or infinitely many. So there are different ways we can do. For example, I have some pattern and regularity going on within the natural numbers. So you might see these people write 1, 2, 3, 4, and then put comma and then 3 dots and then close this. Okay, so that's one way of writing the set of all natural numbers. So these 3 dots means that this pattern will continue forever. Okay, so then this set has a name because that's a very famous set in mathematics. Whenever something is so famous, they give it a name, in this case the set of natural numbers, and they also symbolize it with some symbol that everyone, by looking at it, they realize what they're talking about. In this case, n is a good choice because it consists the first name of natural numbers, but you have to put also another line here. So whenever you see this symbol, it's not just any n, it is the set of natural numbers. So by looking at this symbol. Okay, so this is the set of natural numbers. Okay, and then the set consisting of all integers, okay, or the set of integers. So what are those sets? You can write it in this way, for example. You can write it as, this is not a good way to write 0. Of course, some people write it like that, 0 plus or minus 1 plus or minus 2 plus or minus 3, and then put 3 dots. So this is the set of integers. But to be honest, this is not a very precise way of doing it, because when you write plus and minus, you mean 2 elements. You are supposed to separate elements by commas. Okay, so this, if you want to respect what I told you, so you write, for example, minus 2, and then minus 1, and then 0, then 1, 2, and then you continue forever from the right-hand side. And of course, in this case, you continue forever from the left-hand side. You see these kind of things in math books, okay? Because in this case, we have a pattern, so we understand what is coming next and what is coming after that, and we also know what is coming before that. So this set is also famous in mathematics. We call it the set of integers, and we denote it by letter Z because it is coming from the word Zahlen, I think, in German. And then again, we put another extra line here so that this is not just any Z. It is the Z for the set of natural numbers, integers. Okay? But then hopefully you realize that if I want to define the set of rational numbers, I am a little bit in trouble. Yes, do you see that? I cannot use this pattern. What are the rational numbers? Can you give me an example of a rational number? Yes? 1.5 is a rational number. So if I want to define a rational number, it's a fraction. Okay? So is 2 a rational number as well? Yes. Yes, because 2 can be viewed as 2 over 1, and 2 over 1 is a fraction. But I hope that you agree with me, there is no way that I can use these 3 dots to see the pattern. So what do you want to write? So for example, you can write some of them. For example, I can write 1 over 2. I can write 3 over 5. I can write 7 over 9. Okay, and then of course I cannot put the dots because there is not very organized way or any regular pattern that I can put the dots in and people can understand what I mean. Is that clear? So you see that the same method that we had before is not properly working here. So we have to have another way to actually write my set down. And that is the mathematical description. So what we do, we say that, okay, what is a rational number? A rational number is a fraction, but not any kind of fractions. For example, do you see that this is not a rational number, even though it is fraction? Why? Because its numerator is not an integer. So a fraction whose numerator and denominator are both integers, that is called a rational number, not any fraction. Okay, so I would say that I am interested in all x's, okay, but not all x's. What x's? Such that some books write this vertical line and some books just put semicolon. It doesn't matter. So I think in your book they are using semicolon, but I'm used to write it like this. So you see, let me write it, x such that x is equal to a over b and comma, a belongs to z, comma, b belongs to z, and of course one more condition. Do you see what that condition is?
B can't be 0.
B cannot be 0. And then I close the set. So you see, I described completely what are supposed to be in this set. So only those elements called x. If you don't like letter x, you can choose whatever you want to, but you are not allowed to use a and b because I use a and b for other purpose. But if you want, you can write y, such that y is equal. So that is just a typical name that I chose to say that this set consists of elements that I call them x, such that x is equal to a fraction, so such that the numerator is an integer, the denominator is also an integer, and the denominator is not 0. So do you see what does it mean? It means a belongs to z, b belongs to z, and then I hope that you agree with me, if you can read this correctly, if I ask you, is 1 over 5 in this set or not? Is it there or not? Yes, because this is fulfilling all these conditions. First of all, it is a fraction. Okay, so it satisfies the first condition. The second condition, the numerator is an integer. Is that right? It's a heltal, yes. The denominator is also an integer. That's also true. And finally, the denominator is not 0. Because this number satisfies all the properties I listed here, this means that this number is definitely there. Okay? And of course, if I write square root of 2 over 2, do you think that this belongs here?
No.
You say that, okay, it is a fraction, so the first condition is fulfilled, but I have to have 4 conditions for my number so that this number get a visa for this set to go in. Okay? The first condition is met, okay, but the second condition is not met. So I don't even bother to look at the other ones. Okay? Because in order for this number to get the visa to go to this set country or whatever you call it, it should satisfy 4 conditions simultaneously. Even if one of them is not met, this doesn't get the visa to go. Okay? Is that clear? So this set is called the set of rational numbers, and then we denote it by Q, but we also draw another line here. So this is not just any Q, this is exactly this QB. Okay, so that my point, these things could be a little bit complicated or not, but the problem is that if you want to represent or describe your set, either use these dots sometimes, if the pattern is really clear and not ambiguous. But sometimes it is not possible, then you have to describe it mathematically. Okay, is that clear? For example, so let me write A is equal to the set of all Z such that Z is equal to N over N plus 1 and N belongs to N and N is greater than or equal to 1 less than 4. Okay, so I want you to, first of all, the first lesson is very simple. The lesson is that when you see this, you can read it properly and you understand what are the things inside. Okay, so is that clear? How should I read it? The set A is equal to a set consisting of elements that I call them Z. But which type of Z's? It comes after this vertical line. That Z should be a fraction of only this form, N over N plus 1. If I stop here, it's not complete because you might ask then what n is. So the rest of it, I'm describing what n is. I am telling you that n belongs to the set of natural numbers, okay? And n lies between 1 and 4 with the possibility of n equals to 1. Okay, so that is the description of the elements of my set. Okay, and then might be I ask you, okay, write down this set with elements. List all the elements. So what should we do? So what is the first element? Because I can consider these two conditions together, I would say that you are telling me that n is a natural number on the one hand. On the other hand, n should lie here. So there are not that many options. From these two conditions, I conclude that n could be what? 1, 2, or at most 3, but not 4. Yes? So it means 1 or 2 or 3. Okay? But now be careful. You are not allowed to put 1, 2, and 3 inside the set. Because the set is not n. The set consists of z's. So you have to calculate z's and put z's in your set. Okay, so this letter is important. Okay, so what is z? If n is equal to 1, what is the z? Z is equal to 1 over 1 plus 1, which is 1/2. And then when I say n is 2, so what is z? Z is equal to 1 over 2 plus 1, which is 1 over 3. And then when finally n is 3, then becomes z is equal to what? 1 over 3 plus 1, and that is 1 over 4. So finally, the answer to this problem that I told you is A equals to, how many elements are there? 3 elements.
Oh,
Yes.
it should be 2 over 3 and 3 over 4.
Oh, okay, thank you very much. This is n over, thank you. Okay, so that's good that you saw that, thanks. Okay, so how many elements are there? 3, but not these. Do you understand why not these 3? Because the set consists of z's, not n's. Okay, so then what should I write? I should write 1/2, 2/3, and 3/4. So 1 over 2, 2 over 3, and 3 over 4. And this is the only, not the only way. If you want, you can just replace them. But this is one way of writing. But you have to put curly brackets. A square bracket is not acceptable. Parentheses are not acceptable. And then you have to put commas. Semicolons or things like that are not acceptable. Okay, so that's the set. Is that clear? It's not hard. So for example, if I want to, I can say 1/2 belongs to my set. That is true. Okay, what do you think about this one? Is it true or false? It's also true. It's claiming that the square root of 2 does not belong to the set A, and it's a true claim. So that's also true. One fancy name that you need to learn here, of course this becomes deeper than that, but because you don't study more advanced set theory, it doesn't seem very plausible for you. And that is the word cardinality. It's a big name for what very simple thing at this level, of course. And that is the number of elements, that's it. When I say what is the cardinality of set A, I am telling you how many elements are there within the set. And for the cardinality, we can have a little bit of unfortunate symbol. The symbol is exactly as absolute value. Okay, so I put absolute value. This is not absolute value. In this context, it is called cardinality. Then I put a set inside. Whenever this you see within these two symbols, which is similar to the absolute value, you have a set, it means it is cardinality. Yes? So if I say this is A, and I write this immediately, of course I do not mean absolute value, because absolute value is meaningful when I put a number in. but I have put a set there. So this means cardinality of set, and this means count the number of elements. That's it. So what's the cardinality here? Yes? Okay, but if I ask you the same question, that is why the people who actually discussed about these things, it is more than that. So if I ask you what the cardinality of n is, what do you say? Yes, the cardinality of n is infinite. So I mean, so even you cannot say that, we can say that this is an infinite set, okay, because the cardinality is infinite. So these are examples of what we call infinite sets. And this, for example, here is an example of a finite set. So when I say I have a finite set, it means I have a set that I can count the number of elements. For example, if I consider the set of all human beings, is it finite or infinite?
Finite.
Finite, but it's a huge number. The cardinality is huge, yes.
Isn't the infinite of integers larger than the infinite of...
Yeah, that I want to discuss a little bit. This is not part of the course, but that might be fun. Okay? So when it comes to finite numbers, ordering them is not hard. If I give you 3 and 4, you know 3 is less than 4. If I give you, I don't know, even if I give you square root of 2 and 2, which one is bigger? Of course 2. Okay? But when it comes to infinities, it is not easy at all. Okay? So you see that the set of integers, if I ask you what the set of integer is, what is the cardinality, you say infinitely infinite. And what is the cardinality of the set of integers? That's also infinite. That was a very interesting question for mathematicians to see if there is any difference between infinities here and there. Is there the notion of a bigger infinity? Something like that. Okay, so it was not easy. I mean, how do you want to see which one is bigger? And 99% you make a mistake and you say that the infinity in Z is bigger. But the surprising answer is that the infinity in N and Z are the same. So, but you might say, how can you say something like that? By the way, it's not very complicated. I can try to give you a little bit of flavor. Not for this a little bit complicated one. I can give you a little bit simpler example. For example, let us consider the set of natural numbers. And then one group of the natural numbers are even numbers, one group of natural numbers are odd numbers. If I say how many odd numbers are there, what do you say? Infinite. If I say how many even numbers are there, and how many natural numbers are there? Infinite. But what is your intuition about these infinite sizes of these infinities? If I say the number of the size of odd numbers, the size of the set of odd numbers equals to the size of the even numbers, it's not that surprising. Yes? Surprising thing is that if I say you the number of even numbers is equal to the number of all numbers, all natural numbers, then it becomes a little bit surprising. But you can understand it. It's not hard, you know. Because the notion of numbers, so let me so let us consider this case. Let me list the set of all natural numbers here. 1, 2, 3, 4, 5, 6. Let me do it the other way. Okay, so that's good. And then let me list the even numbers. 2, 4, 2, 4, 6, 8, 10, and continues. The first intuition is that these two infinities cannot be of the same size because it is a sub-collection of what you see there. Okay, but how can I convince you that they have to be of the same size? It is not that hard. What we do, Consider this scenario, okay? So let us say that I have students outside the aula, but let us imagine that we have infinitely many people outside, okay? And then I have infinitely many chairs in the aula, okay? So the people there are waiting for me to tell them where to sit, okay? And I assume that I have labeled these chairs with these numbers 2, 4, 6, 8, 10, etc. Okay, so I didn't label them 1, 2, or 3. I labeled them 2, the next seat 4, the next seat 6, etc. Okay, and the students are there, and I labeled them 1, 2, 3, 4, 5. So they come and I give them label. I give them the first one 1, the second person 2, the second. Okay, and what I do, I will tell them that, okay, you go to the aula because we have infinitely many people here to keep the mess, to prevent that a mess happens. Follow my rule, okay? Read your label, whatever that label is, multiply it by 2, and go and find your seat in the aula. So if they follow my rule, the first person takes the label, it is written 1, it multiplies it by 2, it becomes 2, and then when he comes in, finds the first place 2 and sits down there, okay? So that person, 1, takes which seat? 2, okay? So the second person, number 2, takes the label, reads it, it is 2, multiplies it by 2, comes in and takes which seat? Number 4. Okay, and then the third person takes it and it becomes 6. So this is the question. If they follow my rule, do you think that there will be a person without any chair, without any seat? No, because any person labeled n, multiply this by 2, it becomes 2n, and 2n is an even number which is somewhere listed here, and that person finds a seat and sit down there, okay? So it means that every person will find a seat to sit down. Is it possible that if they follow my rule, 2 person will want to take the same seat? No, it is not possible. Yes? Do you think it is possible that a seat is left empty after, of course, this you have to imagine, this is not in principle possible, but let us say that this is settled down, okay? Do you think that a seat will be left empty? Yes or no?
No.
No, no seat will be left empty. If you say a seat is left empty, you need to tell me which number is left empty. Which number is left empty? Is number 10 left empty? No, because it is occupied with which person?
5.
5. Is, I don't know, is 19 left empty? 19 is not my list. Is 20 left empty? No, it is occupied by 10. So what does it mean? It means that I have infinitely many people outside and infinitely seats inside. But what is happening? After everything is settled down, don't think it physically, because infinitely many people needs infinitely many time to arrange, but forget about time, okay? And it means that every person find one and only one seat to take, and no seat will be left empty. So what is your conclusion?
The infinities are equal.
Yeah. So that is the meaning of being equal in size. Okay? So because this is exactly the way, because when we have finite, for example, let us say that I have 10 people outside and 10 chairs inside. I can do the same trick. Do you agree? I can do the same thing, but I will never do that. I will count them. I say that there are 10, and count the chairs, there are 10. If there are 10 chairs and 10 people, I know that this will be arranged. Okay? But when it goes to infinitely many, I will not be able to do it like this. I cannot count infinitely many peoples because it will never finish. And I cannot count infinitely many chairs. But I can convince them by this very simple argument that I am on the safe side. No chair will be left empty and no people will be wandering for a chair. Yes, is that clear? So the only conclusion that I can make is that, okay, the number of infinity many people here and the number of infinitely many chairs here, they have to be the same. even though it is extremely counterintuitive. Is that clear? So I don't want to go through this topic anymore, but I wanted to tell you that this is not a very surprising, this is not very hard thing to understand. It was very simple to understand. Of course, you still resist sometimes because your intuition is developed. But for example, here, that is it's more surprising here. If I ask you the same question for Z and N, you might say that, okay, Z, the number of elements in Z is more than the number of elements in N. But similar to this argument, you can prove that no, the number of elements in N, of course the number in quotation mark, the number of elements in N and the number of elements in Z are the same. But the rule that I have to establish is not very straightforward. You have to be a little bit creative. So if you want, you can think about it. It's not a hard problem. So you see that I have people's outside labeled with natural numbers, but I have seats inside the aula labeled by integers, -0, -1, -2, 0, 1, 2. And then you want to design a rule to tell your students how to sit down so that there is no problem there. The rule that you have to invent is a little bit harder than the rule that I invented here, okay? But it is possible. And by the way, if you cannot invent a rule, it doesn't mean this is not true. It means that you couldn't invent the rule. So this is that the reason that I told you is that because it is a very hard matter to prove that two infinities are not equal. Because if you want to prove two infinities are not equal, you have to guarantee that there is no such a rule that anyone can come up with, and that is very hard. Because you might say that, okay, I was not smart enough to find the rule. Might be another person who is smarter comes in and find the rule. So if you want to say that, no, one infinity is bigger than another infinity, you have to be even smarter to say that, okay, it is not possible, not just that I couldn't find. Okay, so that's a very hard subject. It's not that easy. But then, for example, another surprising thing that you come up with, so you know that if I have a line segment, it consists of points. How many points? No, line segment, the whole line segment. Infinitely many points. All the points on the line segment. Yes, this is just the initial point and the end point. But if I ask you, a line segment consists of how many points? Infinitely many points. Okay, let me draw a little bit longer one. So how many points are there? Infinitely many. But do you think this infinity is bigger than that infinity or not? Yes or no? Okay. So there are infinitely many points here. There are infinitely many points here. But again, the sizes are the same. And I can convince you. That is a matter of logic. Okay? I am claiming that the number of points, the number is a bad word, but I hope that you understand what I mean. The cardinality here and the cardinality here are the same, even though it is counterintuitive. It seems it is longer. It should include more points. But can you see why not? Can you establish a rule, as I told you? This rule, by the way, that I established, it is called one-to-one correspondence. Okay, so I just established a one-to-one correspondence between the students and the chairs. So they know where to go and where to sit. So here, can you establish a one-to-one correspondence here as well? Okay, so this is a little bit tricky, but it is fun, I think. So let us take this endpoint and endpoint and connect them with my ruler and extend that. I do the same thing from here, and then I extend that. So, and then let me clean what I don't need. Okay, so now I want to establish my rule. It's a one-to-one correspondence. So I say that I take one point here, and I assign exactly 1 point here. How? I say that connect this one to this one and continue the line. It will go and intersect this point. So I say that this point, let us say this point is a person, this point is a chair. So I tell you that this person have to go and sit on this chair. Okay? So again, what is the next person? I take my ruler, connect this one to this one, and go, and that, so this means that person has to sit on this chair. Okay? So can you tell me which seat is occupied by, which person occupies this seat?
Okay, right.
So how can I find it exactly?
Take the ruler.
So take the ruler and then connect this one to that one, and then I get a point here. So you see, every point here corresponds to exactly 1 point here, and vice versa. Every point here corresponds to exactly 1 point there. So the sizes should be the same. If not, you need to tell me a point which cannot be connected to this point, or you should give me a point which cannot be connected to that point. But this is not possible. So then you have to agree by the rule of logic that the number of elements there and the number of elements there are the same. And then you see that wide number of elements is not a good idea, because there are infinitely. So this is why they invented the word cardinality. So the cardinality here and the cardinality here are the same. Okay? But that is not part of your lesson, even though it was not very hard to understand. Yes?
Couldn't one point be connected in that?
No, you see, if I can establish one single rule that it works, it guarantees that the number of elements are the same. Okay? Of course, I can mess up. I can just distribute labels randomly, and then they want to come and sit, they will fight over the seat to sit down there. Okay? But if I can establish one single rule that assign every person to exactly one chair, not more, then it means that the number of elements are exactly the same. Okay? Okay, it is exactly. So here, you might say that there are many rules that does not work. Yes, I agree with you. But there is at least one single rule that works, and it shows that the number of elements should be the same. Yes?
Isn't it possible for 2 points on the longer line to connect to the same point on the shorter line?
No. If you follow my rule. Do you understand what I told you that? So which 2 points here?
I mean, like really, really close points.
No, even really, really close points. So for example, I cannot, so this point, and this point. If they are not the same, the line that I draw from here will not be the same line that I draw from here, even though they are very close. Okay, what you are saying is that the distance between the corresponding elements will be even shorter than this one. But anyway, there is a distance there. Okay? Okay, so this is one thing that we want you to know. So what the notion of a set is, it is a primitive notion. We don't insist to define that, but we have a good idea what is going on. For example, let me ask you one question again here. Is it a good thing to say the set of all prime numbers? Is it a good description of a set or not? Prime numbers is a good example because we don't know all of them. Okay? But is it a good description? Can I say the set of prime numbers consisting of prime numbers? Okay, so for example, I write this and I ask you, is it a correct description of a set or not? What do you think? Yes?
No.
You say no. Another answer. Is it a good description of a set or not? Rely on your information, not intuition. Have I talked about the set of prime numbers before? Okay, so forget about information. Just think about it. Is it a good description? It's a good description. It is a good description, okay? Because you might write a number, okay, that you don't know is it a prime number or not. But you know that it is either a prime number, which is in my set, or not, and it is not in my set. So there is no ambiguity. Might be I don't know at the moment, but it is different from saying that the set of some natural numbers. Do you understand what I mean? If I say the set of some natural numbers, there is no way for you to understand if 52 is there or not. It doesn't depend to your knowledge. By nature, by construction, it is not possible to understand if this is true or false. Okay? So that is the reason that I told you, because I might think that I thought that you might get confused. Okay, but the set consisting of prime numbers is a good description of a prime number, because technically speaking, either a number is a prime or not a prime. If a prime, it is there. If it's not a prime, it's not there. Might be it is hard to understand if it is there or not. But I didn't say it should be easy to see it is there. It should be the case that any element, any object in the world should be either there or not there, even if at the moment I don't know which one is that. But it is not impossible in principle. Yes? So the set consisting of prime numbers is actually a good description of a set. Now, do you remember, is this set finite or infinite? We proved that. Do you remember that was the elegant proof of Euclid, who showed that there are infinitely many primes out there. So it means that if I collect them in one set, that set will be infinite. Okay? Okay, so then the other set that we have is the set of irrational numbers. What is the set of irrational numbers? We will talk about that a little bit later. But irrational numbers are the real numbers that are not rational. If I have a number, but it is not here, I call it irrational. Okay? So there are two symbols for that. Either you use I for irrational with another line, or you will see why. People sometimes write it as Q, but they put a C there. This C means complement. I will talk about that later. Okay, and then the set of real numbers is what? Denoted by R. So we haven't studied even in math for complex numbers yet. So the set R is the set of all numbers that we know. Any number that you can imagine before studying complex numbers is a real number. Okay? And if I say what is irrational number, definition of irrational number is a real number that is not rational. That is called irrational. For example, the famous one is square root of 2. We studied this before. And there are two more famous ones, the famous pi number, and the Euler number. Okay, these are very famous irrational numbers. It is good to have in mind. Okay, and then we just talked about cardinality. So if I ask what is the cardinality of R, what do you say again? Infinite. But it turns out that the cardinality of R is much bigger than the other cardinalities that we have learned. So the cardinality of R is really a higher infinity. Okay, I just want to pass you as information. These are not part of your lessons. But again, surprisingly, if I consider this line, only the numbers from 0 to 1, all the numbers from 0 to 1, including 0 and 1, and consider the whole real line, what are the cardinalities between them? The same, exactly as the argument there. So between 0 and 1, there are as many numbers as you can imagine, that is in the set of R. So the cardinality of the numbers from 0 to 1 and the cardinalities of R exactly the same. So this means that the cardinality of the numbers between 0 and 1 is even bigger than the cardinality of Z. Okay? Okay, so I don't want to bother you about these things, but this is the reason that now you understand why cardinality is meaningful to talk about, because that's not just finite numbers. But in your lesson, you have this word, but only for finite sets, and that is very simple. Just count the number of elements there. Yes? Is that clear? Okay. So let us see what we have again here in the book. Okay, so there is another notion which is called the subset. That is very important to understand, a very important concept. Before doing that, there is a set without anything inside. Okay, so it means that you open the curly bracket and you don't put anything inside and then close it. Okay, so this is called the empty set. It's a good name for it. So the empty set. Okay, and it is denoted by this, or we have a Greek letter for it, and that is this symbol. Okay, so when you say this is Greek letter phi, I think so, but anyway, or it is very close to this. This is the symbol we use for it. So we say this, the set is the empty set. So if I ask you what the empty set is, it is a set consisting of nothing. Okay, one caveat is that some students, when I say write the empty set, they mix things. This is not the empty set. If I want to give you a feeling, let us have a bag, nothing is inside. But now I have a bag, inside my bag there is an empty bag. The bag inside is empty, but the outside bag is not empty. What is inside? It's an empty bag inside, yes? So this is a bag containing of an empty bag. So the whole thing is not empty, so be careful. Don't write this for the empty set. Okay, so if I ask you what is the cardinality of the empty set, what do you say? The number of elements in the empty set is 0. So the cardinality of the empty set is 0. But if I ask you what is the cardinality of this, what is the cardinality of this? 1. What is inside the set is an empty bag. So there is one object inside my set, and that is the empty bag. So the cardinality here is 1. And be careful, they are not the same. So this is not the empty set. How many? So if a set contains exactly one element, that is called a singleton. Okay, so that is one thing that is important to know. Another thing is the notion of the subset. Okay? The notion of the subset. So let us consider two sets. One set A, another set B. Okay? Two sets. We say that A is a subset of B, and we denote it with this symbol. Okay, so how do you read this? We say A is a subset of B. Yes? So what do I mean by this? I mean, whenever you see this symbol, the person who has written this is telling you that whatever element is in A, it is also in B. Okay? So if I want to write it in symbols, it means, do you remember the symbol I used for all? X. If X belongs to A, then X belongs to B. In your book, they haven't used this. They have written only this part. But in principle, you have to write this as well. So when I say A is a subset of B, I mean whatever element you find in A, you can also find in B. But don't think that they have to have the same elements. For example, very simple example, I give you a set A, 1 and 2. This is a set with only 2 elements, 1 and 2. Let me give you another set with 3 elements. For example, 2, 1, and 5. Now, this set is a subset of B. Why? Because whatever element you see in A, it is also in B. You find one in A, is one in B? Yes. You find two in A, you also find it in B. So whatever element you see in A, it is also in B, so we say A is a subset of B. So if I write this, and I write this, for these two sets that you see on the board, you see this one is true, but this one is false. Do you see why this is false? B is not a subset of A. Why? Because there is at least one element in B which is not in A. And what that element is? 5. Yes? So B is not a subset of A, but A is a subset of B. Is that clear? Okay, if I give you two sets, but I don't tell you what is this set, without telling you, how do you evaluate this statement? Can you be sure that this statement is true? Can you be sure that this statement is false? Or, depending on the situation, this statement could be true or false. Here I told you what A is by writing the elements. I told you what B is by writing the elements. But here, I am telling you that I picked up a set in my head. I don't reveal the elements. Then I write it down. Without looking into my head, can you say this is true or false? Yes?
It's true.
It's true. Yes, do you agree? Because when this becomes true? It becomes true whenever everything in this left one is also in the right one. But because A and A are the same sets, whatever in the left one is automatically on the right one. So what is the moral here? You need to write it in words, okay? Every set is a subset of itself. Yes? This is something I want you to remember. Okay. So another thing, let me ask your understanding here. This time, I tell you that I pick 3 sets in my head. I don't reveal what is inside them, but I guarantee you that A is a subset of B, okay? And B is a subset of C. Okay, I guarantee them. And in my notation, I use this for and, yes, and this for or. So I guarantee you that A is a subset of B and B is a subset of C. Now I want you to evaluate this if possible.
It's true.
Okay, is this true or false, or it is depend to the situation?
True.
It's always true, yes? Because what is the meaning of this? It means whatever is in A, it is in B. I guaranteed that for you. And I also guaranteed that this one for you. What is the meaning? It means whatever in B is automatically in C. Okay, then what happens? Whatever in A is also automatically in C. Because if I choose A, why is that true? Because if X is in A, because A is a subset of B, from these two, I can conclude that X belongs to B. Now that X belongs to B, I use the second piece of information that I gave to you, and then it means that X has to be in C. So I started from assuming that X belongs to A, I was able to conclude that X belongs to C as well. So this is also true, yes? So remember that for every 3 sets, for every 3 sets, A, B, and C, such that A is a subset of B and B a subset of C, then A is a subset of C. I mean, I am writing them down, but this is so simple that you don't need to memorize. It is very trivial. But this property is not always, so let me ask you this question. It's a little bit tricky question, but let me see how you think. Okay, so so far when I wrote a set for you, I write it with simple elements here, but I can also have a set whose elements are other sets. Okay, for example, I can write a set A, and then I open two bigger curly brackets, and then I put this curly bracket in and close it, and then comma, I open this one and write it like this and close it. Okay, before I explain it to you, do you have a feeling? If I ask you what is the cardinality of A, can you answer that question? Do you see that without explaining? Because consider this, you have a bag. Inside that bag, you have two other bags. Okay? One bag contains one pin, and the other bag contains two pins. But if I ask you what the cardinality of the bigger bag is, what is the cardinality? You just open it and see two objects there. So the cardinality is 2. But of course, so the cardinality is 2. But if I ask you, let me ask you this question. What is your intuition about this? This claims that 1 belongs to A. Is it true or false? True or false? When I say belong to it, it means that you just open the bag. And what you see there is not 1, is 2 bags. So 1 belongs to it, this is false. Yes? So if, again, 2 belongs to A. True or false? False. Yes? But now if I say curly brackets 1 belongs to A, true or false?
True.
It is true. And if I say that curly brackets 1 and 2 belongs to A, is
True.
True. Is that right? Okay. Now can you write a set for me so that this and that are true? This set that I wrote here, one of them was false, one of them was true. But let me write another set so that 1 belongs to B is true, curly brackets 1 belongs to B is also true. Can you imagine a set that for that set both of them are true? So what does it mean? It means that when you open the bag, in the bag you see 1, you also see curly brackets 1. Yes?
1, then comma,
1 and comma,
curly brackets.
curly bracket,
1.
1, curly brackets closed. If you want, you can add something more, but if you don't want, you can just close it. Yes? So for this set, both of them are true. Yes? Okay, so now my question for you is this. I want to compare it with what I have written here. This was true. If A is a subset of B and B is a subset of C, I am allowed to conclude that A is also a subset of C. But let me ask you this question. A belongs to B, not a subset, and B belongs to C. A, B, and C are different sets, or any 3 arbitrary sets. But I guarantee you that A belongs to B. I also guarantee you that B belongs to C. Do you think you can immediately conclude as before that this is also true? If you say yes, you have to bring an argument. If you say no, do you remember what should we do? Counterexample. So you need to provide me a counterexample. What is a counterexample? You need to bring 3 sets A, B, and C to me so that the first one is true, the second one is true, but the conclusion is false. Okay? So first of all, you need to think to convince yourself if this implication is possible. If no, give me examples. Which one do you think it is true? Melvin, you said it's false. So it means that you should have a counterexample. Do you have that?
Yeah.
Okay, so let me write your example. So you are telling what? So you need to tell me A, you need to tell me B, you need to tell me C, so that you respect this, but you violate this. Okay, so
if A is curly brackets just 1,
1,
then B is curly brackets and curly brackets 1 inside.
that's it.
Yes. And then C would be curly brackets 1 closed.
Yes, thank you. Is that understandable? So let us check. Do you think A belongs to B is true or false? What is A? A is curly bracket 1. And when you go to this bag, open the bag, what do you see inside? Curly bracket 1, which is A. So this is true. Okay? What about B belongs to C? You go to C, you open the bag. Opening the bag means removing the farmost curly brackets. When you move it, what you see inside is this guy, which is exactly B. Yes? So that's correct. But does A belong to C? Again, you go and open the curly brackets. So you open the bag means removing this. What is left for you is not A. Okay, so A belongs to C is false. Another example, for example, I belongs to Sweden. Sweden belongs to the United Nations. It doesn't mean that I belong to the United Nations. Okay, so be careful. This property, I want you to just hear the name. Okay, so that's called transitivity. Transitivity. So we say that this relation is transitive, but the relation belonging to is not transitive. For example, equality in numbers is transitive. Why? Because if A is equal to B, B is equal to C, I can conclude A is equal to C. Congruency relation in number theory is transitive. Because if A is congruent to B, B is congruent to C, do you remember I am allowed to conclude that A is congruent to C? I mean, this less than equal to is also transitive. If A is less than or equal to B, B is less than or equal to C, I can conclude that A is less than or equal to C. So the moral, the take-home lesson is that subset relation is transitive, but belonging to relation is not transitive in general. Okay? But let me ask you another question. When you say something is not true, it means it is not always true. You might find an example that exceptionally that thing is true. Okay? So when I say something in mathematics is not true, it means that I cannot rely on it every time. Okay? So that is not something that I can use it blindly. But immediately you can cook up 3 sets that for all of them they are true. Okay, so you can do that exercise yourself. Okay. This one is the hardest one that usually students find very counterintuitive is this, which I want you to remember. So we learned 2 properties of subset relation yet so far. One of them is that every set is a subset of itself. The second one is that the subset relation is transitive. The third one, which is very counterintuitive for the novice students in mathematics, is that what do you think about empty set and a given set? So you see, I tell you that I pick up a set, but I don't reveal the elements for you. And you know about the empty set, that's just the empty bag. Now my question is that if I put this symbol between the empty set and the set that I picked up without revealing the elements, do you think that this is true? Do you think this is false? Or you think the information is not enough to conclude if this is true or false? Hmm? It's not enough. Then another problem. I'm just waiting. That's one opinion. The information is enough and it is also true. Okay? So be careful. Why? Because we have to use proof by contradiction here. Okay, so let me ask you one question. Can you tell me, when I say, let us review, when I say A is a subset of B, what do I mean? I mean every element in A is also an element of B. Now, can you give it an English sentence for me to describe this symbol? This symbol means not a subset. Okay, A is a subset of B in English means every element of A is an element of B. Okay, A is not a subset of B. Can you read it in English? What does this mean? Yes? Not?
Not all of the elements in
Okay, a little bit better English. That's correct.
Not all elements in A are in B.
Don't use the word not. Yes, that is correct. But if you want to use not, yes,
Every element of A is not.
you have to use not, but not in the beginning. Let me correct myself.
Every element in A is not an element.
No, this is a very big mistake. That is what I'm asking. You started with every. Okay? What you said is correct, but you started with the word not. Now my question is, rewrite your sentence, but don't start with the word not. Start with there is. Okay, I want you to read this in English, but start with the phrase there is. Yes, Nazanin, you are.
there are elements in A which
No, are is not. I told you, start with there is. There are, by the way, is not correct. Yes? Because you are taking it for granted that there are more than one element with that property. No, we cannot know that. Yes? Yes?
There is an element in A that is not an element in B.
Yes. There is an element in A which is not in B. That is the meaning when you say this is not a subset. Everyone agrees? Okay. Let us go back. I claimed that this is always true regardless of what A is. If you agree with me, fight is over. You remember this phrase, I had it before. If you disagree with me, what does it mean? It means that you insist on its negation. Yes? I am claiming this is true. If you are okay with that, fight is over, that's true. If you don't think that this is true, then it means that you are defending the negation. So when you say this is not true, you have to admit the negation is true. Do you agree with me? Yes or no? Okay. But what is the meaning of this being true? We just said the sentence. It means there is an element in the empty set that is not in your set. But this is not possible because the empty set does not have anything. Okay? So we say this is vacuously true. Okay? It is vacuously true because if you say this is not true, then you have to admit the opposite is true. But the opposite is true as you just told it yourself. It means there is something in the left one which is not in the right one. But this is not possible because the empty set does not have anything. Okay? So this is the way that you have to understand it. This is just based on logic. So if I want to review, we have 3 rules that I want you to send in your memory because these are not in the formula sheet. Okay? So you have to have an understanding. Every set is a subset of itself. For example, do you think this is true or false? True, because I just told you every set. Empty set is also a set. So every set is a subset of itself. And then I told you that the subset relation is transitive, meaning all these sentences. The third rule is that the empty set is a subset of every set. Okay? So these 3 rules that you have to remember. Is that clear? Okay. So I think it's a good point to stop here. We continue I think one more session I will teach, and then I will give you 2 more sessions to practice for the exam. Okay? Any questions?